All right, and it's gonna be beautiful sunny weather apparently for like another week and a half. So this is for Thursday is our first celebration. And the first page is just 4 pages and it's all show your work. First page is this. So you're gonna make just one drawing. You are not gonna make the drawing like this though. This one, if you have more than 11, you do the alternate drawing. So the lower one is the same. You do your outside as a 2S and 2P. And the test is 2 hours. We'll talk about that when we do the review. And on this one, this is the one where it flips, but not the anti-bonding. So the sigma 2p comes first, then the pi 2p. It doesn't change any of your answers, but I really should change questions 9 and 10. So, all right. It does change your answers if you flip it and it's not supposed to be flipped. So the regular one would have our sigma, 2s, sigma star 2s. You will definitely get the wrong answers. If you flip when you're not supposed to. So my recommendation is you just draw the normal one, like I'm doing down here. And the only question that you're going to be asked is this C, which ones have the alternate, and that's this. When you have more than 11 electrons. So once you start filling in the anti-bonding, so normally it's pi and then sigma, and then pi star and then sigma. Once you start filling in the anti-bonding, once you get to 11 electrons, it flips, it destabilizes the pi 2p. So it becomes so much less stable, it ends up higher. So for oxygen, we would have 12. So 2 for, on the midterm, you just have to draw it one time and then you can count from there. So 2, 4, 6, 8, 10, and then we'd have 11 and 12. And this guy will have the 13th one there. So this is our 12. And using different colors can be really helpful. So magnetic qualities, they are both para. So para and para. On the celebration on Thursday, it's going to have boxes to fill in, like your worksheet. That makes it easier for me and it makes it easier for you to know. And so they both are paramagnetic because they have unpaired electrons. The number of sigma and number of pi bonds. So for the oxygen, they both have 1 sigma. For the O2, the pinks destabilize half of each of the pies. So you have 2 half pies. So again, pumpkin and cherry, whatever you want. And then this one, you've destabilized 3 out of the 4, so you only have half a pie. And then the bond order is the total of your, it's just the total of your sigma and pi bonds. So you get a 2 and a 1.5. Or you can do bonding electrons minus anti-bonding electrons. These guys down here have canceled each other out. But if you don't draw the 2 S's, you end up counting wrong. And when you do the one drawing on your worksheet or whatever, you can also fill in the outside showing the oxygen. This is what I meant is which one's longer. And the O2 is the stronger and shorter one because it has a higher bond order. And so the O2 negative, the superoxide, is the longer one. All right, any questions with that first one? All right, for this, I just figured out this is just the number of electrons they each have. And the bond order of 3 would be out of 10. So if you fill in your electrons, 2, 4, 8, 10, that is the only way you can get a bond order of 3 when you have 10 electrons. And so there's 2 of them. So Cn negative and NO positive. So really on your, again, on your celebration, you're going to make one of these, you fill it in, and then you just count your electrons to answer everything else on the page. Don't flip it. Don't draw it like this one up here. Draw it the normal way. So paramagnetic are going. CO? Oh, CO, thank you. Yeah. So those guys all have 10. By the way, when they have the same number of electrons, that is called isoelectronic. We saw that last term when we were talking about noble gases, but they use the term here. It just means they have the same number of electrons. And so their diagram comes out the same. So paramagnetic, you're gonna, anything that is an odd number, but it can also happen, like it happened here with 12 electrons. And it can also happen with 2, 4, 5, 6 electrons. So nothing had 6, so we don't have to worry about that. So oxygen, and then the superoxide again, and the NO, I think are the only ones. So again, if you have an unpaired, if you have an odd number, you have an unpaired. And if you got to 12, the one up here. Fractional bond order would be, you would have to have an unpaired. And so that would be the O2 negative and the NO. So this is a fractional bond order. 1.5 is same as 3/2, and it has an odd number of electrons. Even if it's unpaired like O2 up here, it still will come out a whole number if it's even. All right, and then we have to do the highest energy in each one. So I'll just write it up here. So for 8, we have 2, 4, 6, 8. That would be pi 2p. For 10, we have sigma 2p. For 13, we did that up there. Oh, we didn't do the highest, but it is pi star 2p. The other 10 is sigma 2p. 12 is pi star 2p. This is a crazy question. You would be asked for like 1 or 2 of these, but you've got the idea. For 10 again, we have sigma 2p. For 11, we'd have 2, 4, 6, 8. 11 would be sigma 2p. I'm sorry, pi star 2p. 10 is sigma 2p. And then 14, we are 2, 4, 6, 8, 10, 12. We filled in the pi star 2p. So it's whatever has an electron, the highest one that has electrons. And again, you just have to draw it once and then just make a nice, neat sketch. A couple things I do look at with the sketch. So on the outside, you label it, and that, right, are bonding, sorry. So these guys, the bonding orbitals are lower than the atomic orbitals. The atomic orbitals are on the outside. So again, this one is lower. And the antibonding are higher than where we started because they're destabilized. Any questions with that? And again, don't draw this way because you will get the wrong answers if you have less than 11 electrons. And that ends up confusing students. And all right. So my bucket of coal. This question. So when is MO theory desirable? It correctly tells us magnetic property. So para or diamagnetic. And so that is the wonder of the MO theory. If you had a bond order of 1.5 for MO theory, that would tell you it is paramagnetic because it's an odd number. You have an unpaired electron. In valence bond theory, it actually means you have a resonance. So ozone actually looks like this. It has a single and a double. But you don't, a resonance means you don't have a single and a double. You have a 1.5 bond, that you have a 1.5 bond, which is what a resonance is. All right. So questions from that first page. All right. And I know last week when I started teaching the MO, everybody's like, whoa, what is she doing? But it really is. You make one chart and then you count your electrons. So, and we figure out how they fill in. So which are paramagnetic? The NO is para, the CN is para, and that's it. The other ones all had 14, and 14 we're going to be all the way, going to be pretty high up to here. Now, if you did this, like you only have to draw one, you would not get full credit because I forgot to label. So you guys have an advantage. You know, you do get to use your notes, but you want to have everything organized because there is a time limit. So if you sincerely do, I recommend going back and redoing your study sets. There's just 4 of them. And look over your worksheets and also the labs. So the organic chemistry lab was meant to help you to visualize, like when we're looking at bond angles and stuff. So yeah, all right. The highest energy, so for the NO, it's going to be the pi star 2p. Actually, for all of them, it's pi star 2p, except for the CN, it is sigma 2p. So all of them except for CN are going to actually have the alternate diagram. All right, the strongest bond is going to be the highest bond order, and there is a tie for that. So the CN and the NO are going to end up with a bond order of 2.5. So the highest bond order, all the others have a bond order of 1. And again, the way you're, which has the longest bond is all the others that ended up with 14 electrons. So the NO, the O2 negative 2, the OF negative, and the Ne2 positive. If I counted right, they all end up with 14 electrons. Yeah. And so their bond order was 1.0. This is questions that I just pretty much plagiarized from a book, and I guess I never realized how much they all came out the same. These, do any not exist? And the answer is nope. You would need a bond order equal to 0. And then they do not exist. On your worksheet, you're going to have one that does not exist. If it does not exist, it cannot have a magnetic quality. It can't be para or diamagnetic because it doesn't exist. It's not going to have any bonds. It has no sigma, no pi bonds. Its highest occupied is going to be some kind of anti-bonding because it's completely destabilized. Any questions with molecular orbital? All right. Inside the ring, it is a triangle. It is, what's that called? An isosceles triangle. Remember that from like 7th grade or something? Those are 60-degree angles because it's a triangle. It is constrained by that triangle. It's explosive. It is not a stable molecule because of that. The hybridizations are sp3 because they're all single bonds. Everything's making 4, which we would want it to be 109. And that's the comment here, that they're different almost by half. And so it's really constrained. I don't know, whatever word you want to use there. We've really compromised it. It is definitely polar. Reminder, the other word for that is hydrophilic. And I printed in colors, so that's the red area, but without having the color, the oxygen pools. And again, it's a ratio. There's only 2 carbons. So if we only have 2 carbons, we have an oxygen. The oxygen's definitely pooling. So where are the positives? So the oxygen gets to be the negative. If we did it here, we would show the red is negative. And then the positives would be on the carbon area. You can also show it with an arrow pointing always towards the negative. And oxygen is going to be the one that pulls. The only thing that can pull from oxygen is fluorine. Questions with that one? So there's a lot of those on, not a lot, there's a handful of those on the exam where you have a picture and you tell me, not like this one, these are special situations. And then this one's another special one. So when you have two double bonds in a row, it is rotated because it has to do with how the pi bonds form. So this pi bond, the overlap is above and below. So one is overlap above and below, which is why these end up along the y-axis, and the other one, the overlap is in front behind. And so we have on the y-axis, and then this is rotated along the x-axis. And so it ends up not being flat. The hybridizations, these guys are sp2 on the outside because they have, right, 1, 2, 3 connections, and the middle is sp. And oh, the orbitals that overlap. So this last question, they are unhybridized p orbitals. So in the sp, there's still 2 more p orbitals that didn't come in the hybrid. So up here with the sp3, there's no pi bonds because sp3 does not have this. So this is what makes the pi bonds in this theory, in the valence bond theory, is the unhybridized p orbitals. So they're the ones that were along the x, y, and z axes. So their overlap is going to be like that. All right, questions? If not, I'm going to go ahead and stop. And